Hello, this is Rob Ellis from Geosoft. On November the 9th, 2012, I gave a presentation at the Inversion workshop at the SEG in Las Vegas on magnetization, vector inversion and Cartesian cut cell methods. This work that's been done in collaboration with the team at Geosoft and Barry DeVette on the early magnetization vector inversion work. In this presentation, I will make a few comments on modern unconstrained inversion, emphasizing that it has a lot of value in exploration programs. I will talk a little bit about Cartesian cut cell methods and how these are important methods for incorporating surfaces into voxel-based inversion. And then I'll go on and talk about vector magnetization inversion, emphasizing that the magnetization vector is the natural parameter for inversion of magnetic field data, and that it allows us to include the effects of remanence, demagnetization and anisotropy into inversion. I'll compare with conventional susceptibility inversion and then explain how we can use this method in exploration. One of the themes of the workshop, this workshop, was that without a sound knowledge of both the strengths and weaknesses of inversion methods, geophysicists run the risk, as methods become more powerful and easier to use, of over-reliance on a technological black box. And the workshop is aimed at non-specialist geophysicists. So I want to make a couple of comments about this theme. It really resonated with me because I've had a lot of people come to me and say, with Geosoft making inversion so much easier to use and more powerful, just about anybody will be able to run an inversion. We actually think that that is an excellent situation at Geosoft. We want to empower explorers to be able to run inversion in an efficient and effective manner, and what we're trying to do is provide an inversion which has necessary defaults in place so that when the non-specialist geophysicist runs an inversion, they will get out meaningful results that will improve their interpretation process. So how can we improve in confidence in inversion? Well, one way is to simplify and educate. We believe that inversion publications should always satisfy Claerbout's principle and those of reproducible research, and that is basically that anything that's presented should be able to be replicated by anyone who's reading about it. So what we're trying to do is make everything that we present here available on our website, www.geosoft.com, and it can all be replicated within Voxy and Oasis Montage. Further, Geosoft Voxy program is actually free for small models to facilitate a full understanding of modeling and inversion principles. Now, let's take a look at modern unconstrained inversion and what it can add to an exploration program. Unconstrained inversion is important because it is very simple to set up, and it provides a first pass at interpretation of a geophysical data set. Now, consider the dipping plate model that I have shown on the left here. This model has a geophysical survey conducted over the top of this dipping plate, and from that dipping plate a geophysical response will be observed. Now, back in the 1990s, when we had the first introduction of smooth inversion, doing an inversion on this type of data would have been or was extremely tedious, time-consuming and often fraught with failure. Inversions at that time often crashed, didn't converge, and produced odd and unusual results, uninterpretable results. However, now we've moved and understood more about inversion over the intervening 20 years, and we're able to produce much better unconstrained inversions. For example, our 2010 style sharpened or focused model inversion for the dipping plate is shown on the bottom right, and that's a much better image to try and interpret than the smooth model inversion of the 1990s. So we've come a long way in the last 20 years, and modern unconstrained inversion is extremely valuable in exploration. We can go further than this if we know something about our model. For example, that the model is itself probably due to some flat line or a lens-like target, we can tailor our simple inversion to accentuate and incorporate that fact. Now what I'm showing on the left is a flat-lying target with a geophysical survey flown over it, and on the right at the top I'm showing the 1990s style smooth model inversion. You can see that that does pick up the top of the plate, but the general model is deep and indicates something below the true model. Underneath that, the 2010 style inversion, where we've included the information that we want to recover a flat-lying target, shows a much better result. So again, this is a, let me say, almost unconstrained inversion. There's no complicated geophysical constraints built into this. It's very simple to use, or geologic constraints. It's very simple to use, and we're able to focus on the style of target in which we're interested. In the next slide, I'm showing that even using this simple unconstrained inversion, or almost unconstrained inversion, we're able to explore the space of solutions for a particular model. On the left I'm showing a basic prism in a half space, and over the top of that prism a geophysical survey has been conducted. Now what you're seeing on the right are a series of models where I've at the top emphasized that this model should be superficial or shallow. In the second image down, the model is shallower than the true target. On the third image, which is our default inversion, you can see that the recovered model is approximately in the position of the true target, and on the bottom image I've shown a model which I've emphasized to be deep in the section. Now these four different models all show or all have the same fit to the data. So it's very easy now in modern inversion, modern unconstrained inversion, to be able to explore the space of solutions, and this is a very important concept and tool in understanding geophysical data. So what I would say is that even though the emphasis in this workshop and also in research is building detailed constraint models, there's still significant exploration value in a simple unconstrained inversion. The fact that they might be considered black box or easy to use shouldn't undermine their value because of the modern developments that have gone on. These inversions that I've shown you all essentially rely on reweighting or the model weighting in the inversion, and this is brought in through a simple process such as iterative reweighting inversion or sharpening or focusing, and it significantly improves the geometry and physical property estimates. And simple constraints can be used to target particular geometries. I showed you the example of the flatline geometry, and on the bottom of this image again I'm emphasizing just how well these basically unconstrained inversions allow you to recover this dipping plate. That's a very useful and efficient type of process to apply to geophysical data. Now I want to turn to a second topic, and that is improving our Earth models and mesh design. There's currently a lot of work going on structured, semi-structured and unstructured meshes, and we want to introduce a new, well not a new, but another type of process for embedding surfaces into our models. This is called the Cartesian cut cell method. I'll show you how it is implemented and then present some examples of the effects of using this method in exploration. So the motivation for considering new mesh models is really twofold. First, we want to improve the realism of the Earth model and minimize modeling errors. And secondly, we would also in the process like to improve computational efficiency, although this is a less important issue than the realism of the model itself. To date, we have several mesh type structures. On the left I'm showing the regular mesh with a complicated ore zone buried in it, shown in green. And on the right of that, in the center, I'm showing a quad tree mesh, and on the far right an unstructured mesh. Now, in a regular mesh, if we want to represent this ore zone, what we would normally do is turn voxels on and off so that the ore zone would be represented by a blocky type of structure. In the octree method we do a little better than this. It's essentially the same process. However, wherever we want more resolution or better approximation to the surface, we divide the cell of the voxel which the surface cuts in half in each dimension, and repeat that process until we have our desired resolution. And in the case of unstructured meshes, of course, we can make our elements a piecewise approximation to the surface. Now, what I'd like to present in this work is the Cartesian cut cell method. We believe it's a very promising option for geophysical and geological problems. It's basically a subclass of the immersed boundary method and has been in use for, I suppose, 30 to maybe 40 years in one form or another. And in cut cell methods, any cell containing a control surface, such as a topography or a fault or any ore zone boundary, is modified by incorporating that control surface into the cell boundary. So the way that works is, for example, here I have an element which has a control surface, in this case a topography, cutting through it. Now, normally we would either turn this entire cell on or off in our modeling and inversion process, but in the cut cell method what we do is approximate this topography cutting through the cell by a single linear approximation through the cell, turning this into a trapezoid and representing the cell now by the reduced volume associated with the cut cell. So what has happened is the upper boundary has been truncated and cut back to this linear approximation. And you can see there, I can do that in each of these cells, and the topography is extraordinarily well represented in that approximation. On the right of that, shown in blue, I'm showing by comparison what would happen if we use the simpler on-off choice for a voxel, depending on whether the control surface is above or below, say, the center of the cell. So the cut cell method gives a very good approximation, far better than the regular mesh. We can do this, as I said, for embedded bodies as well as topography. For example, here's an ore zone, and in each of these cells around the ore zone, the cell is cut, the cut cell is formed, and that is used in the modeling and inversion. I've shown you how it works in 2 dimensions. Obviously in 3 dimensions it becomes numerically more challenging, although in principle no different. There are 256 ways to cut through a voxel element if you allow 1 cut per edge. And for potential field work we use the cut faces and the corresponding cell faces to form a polyhedron, and then we calculate the geophysical response from that polyhedron. This has an advantage for us in particular at Geosoft because we have a large library invested in voxel-based representations. We have mathematics routines that we can apply to voxels. We have cutting routines for voxels and surfaces. We have 3D display of voxel models. So we want to maintain that library and yet also incorporate the greater accuracy of these cut cell methods. And the advantage is that the model that you obtain with this process is still largely a Cartesian voxel model. So how would that work in in practice. Here I'm showing on the right a hill, gentle hill, with a survey draped over that hill. The survey locations are shown is the orange dots, and what I'm showing in the middle of that hill is a yellow cut cell. This is a cut cell that's been formed by the process I've just described, and it fills in the surface so that the surface becomes a smooth surface rather than the stepwise surface of a prism approximation. So let's zoom in on that so you can see it a bit more clearly. You can see here the cut cell filling in the area which is required to turn this into a smooth surface. Zooming in a little further, now you can see the cut cell quite clearly. The surface is made by 3 triangular facets on the top. Shown behind it here are the volumes which would be filled by the neighbouring cut cells. This leaves us with a polyhedron from the cut cell, from which we can calculate the potential field response and then use in our modelling and inversion. And what I'm showing here on the bottom left is the fact that this cut cell is actually based on one of the 15 examples that I showed you on an earlier slide. So let's now apply this to field data. In this instance, we're going to consider a gravity gradient survey in northern Peru in the Chota province. On the right here I'm showing the location of that in northern Peru, close to Ecuador. The survey area I'll be concentrating on is 12 kilometers in the east direction and 16 kilometers in the north-south direction. It was a nominal drape flown over this at 120 meters. Of course, in this rough terrain, the clearance varies considerably and is often far greater than 120 meters. I'm going to show you simulation of the GZZ response. I will use that particular component of the gravity gradient simply because it's the simplest to visually interpret. And this modelling was done on a 75 metre by 100 metre by 35 metre cell size, and you can see that gives us a good representation of any possible geology. Now in this slide what I'm showing you on the left is the Cartesian cut cell GZZ. So this is the GZZ that's been calculated using the cut cell method, and you can see it's a nice smooth image and looks very reasonable. On the right I'm showing the corresponding image that would be obtained or is obtained by using a prism-based algorithm without any cut cell approximation. So and what you can see in that image is that there are lots of highs and lows. There's a definite noise on the image. These are modelling artifacts from the survey location coming close to or far away from prism edges. So this is a very distracting type of problem because these small anomalies may well be confused with targets and other areas in the survey. Now this simulation was carried out at 120 metre clearance and the vertical cell size is 35 metres. So this is nearly 4 times, the survey is nearly 4 times higher than the vertical cell size. So you can see that even something that you might think was a reasonable distance from the cells themselves is in fact still corrupted with this prism noise. So this emphasizes that the Cartesian cut cell method works very nicely in any areas of terrain. Now here's the corresponding images for a TMI survey, in this case flown on a 30 metre drape. You can see that the TMI image is quite clean and free from modelling artifacts, whereas the corresponding calculation from the prism approximation, the standard prism model, shows significant noise, due to flying close to or far away from prism edges. The actual noise on this image has a standard deviation of about 6 nanotesla, and the actual signal standard deviation is only 13 nanotesla. So the contamination is quite severe. Again, the cut cell method works very nicely and is effectively free from artifacts. Just as an aside, I was interested to see or compare the use of prisms as the elements in the model compared to using prisms. So we're using an equivalent sphere rather than a prism, and the effect of using spheres is somewhat worse than using prisms. However, both are severely contaminated by artifacts, and the computations for the prism responses are very much more time-consuming than spheres. So it seems reasonable to say that using prisms is not really computationally effective because they're still contaminated by so much modeling error. Now, you may think that the cut cell method or the worrying about these issues associated with terrain is important only for models in which there is significant terrain. However, that would not be correct. I'll show you an example here from San Nicolas deposit in central Mexico, where the terrain is quite flat, and you will see that it's still important to use the cut cell methods. This model for San Nicolas was generated by Mara Geosciences as part of a Camiro project. There's a VMS style target in the center of the model. There's a number of different layers in the host, and some faulting has gone on. What I want to show you here is the prism approximation to the surface of the model. You can see that this is quite a flat model. These are 10 meter by 10 meter by 10 meter cells, so a very good high resolution model. And when you have areas of even large flat areas like this of minimal terrain, what you'll find is that there's a large flat area in which the model representation is constant on the surface, and then in the prism approximation you take a step of 10 meters up and then continue on with another large flat area, and then again another step of 10 meters, and so on. So what you see is these 10 meter steps running through the model. What happens if I run or simulate the response over those models? Well, on the right here I'm showing that models zoomed in a little bit, and you can see that when you calculate, for example, the RTP magnetics in this case, in the model, in the response itself, there's a definite evidence of the artifacts, modeling artifacts induced by these steps in the model. And that's these areas shown here, these ridges in the model. If I use the Cartesian cut cell method, which I'm showing on the left here, what you can see on the top is the prism approximation, and drawn over that in wireframe I've shown cut cells which will be used to more accurately represent the terrain, and when I use that approximation I get an RTP response which is free of these annoying modeling artifacts which are present in the prism model. So what I'd like to summarize with at this stage is that the Cartesian cut cell method essentially produces artifact-free responses from airborne surveys, and in many cases is sufficient even for surface surveys, eliminating the need for upward continuation of the data, which always degrades the inversion result. Prism and sphere approximations to the control surfaces, particularly topography, both produce severe artifacts. And this is true unless the element dimensions are of an order of magnitude smaller than the distances between the control surface and the observation point. Even large flat areas benefit from the Cartesian cut cell method to avoid terrain aliasing. We like this style of model because it works well within existing regular mesh algorithms, and it can be used to display and work with any type of surface, whether it be a fault, a closed surface like an ore body zone, or a salt dome. Any of these type of models can be incorporated, or their embedded surfaces can be incorporated in a voxel model. And as one final comment, we should realize and emphasize that modeling errors, such as we've seen here in this prism approximation, must be included in the error specification in the inversion. So when, as a practitioner, when you're running an inversion and maybe the data looks like it has only a 1 nanotesla error, if you've got modeling errors at 5 nanoteslas, these need to be added into the error specification. Now I'd like to turn to a third and final subject in this presentation, that is vector magnetization inversion. In this part of the presentation, I will demonstrate why the magnetization vector is the natural parameter for magnetic field data inversion. I'll talk about remanence, demagnetization, and anisotropy, and I'll compare the magnetization vector inversion with susceptibility inversion. We'll also discuss how to interpret magnetization vector inversion in exploration problems, and I'll demonstrate that magnetization vector inversion can be used with constraints and reweighting, and I'll do that using a synthetic example and show you the application of magnetization vector inversion to field data. Firstly, why do we need to consider an extension to conventional susceptibility inversion? Well, firstly, we've noted that over the years a significant percentage of magnetic inversions yield geologically inconsistent models. And one of the reasons that this might be occurring is because these conventional susceptibility inversions ignore demagnetization, anisotropy, any effect related to remanence, and also any effects related to local field perturbations. And we're also finding from a geologic point of view that remanence is becoming more important and needs to be considered even at a regional scale. So this is a definite indication that we need to go beyond the susceptibility approximation in magnetic field inversion. So let's look at the magnetic field inverse problem. Basically, the magnetic field that we measure, B, in our surveys is due to some magnetization in the Earth, and that magnetization can be represented by a series of magnetic dipoles. Maybe this is in an ore body containing some percentage magnetite or pyrrhotite. In any case, whatever the physical representation is here, we're showing that as a series of magnetic dipoles which can sometimes be aligned with the Earth's inducing field direction, but can also be oriented in other directions depending on the history of the rock. The magnetic field is given by magnetostatic Maxwell's equations, and they are shown here on the bottom of this slide. It's two relatively simple equations. And what we normally do is, or what we can do to solve these equations, if we wish, is to transform them into an integral equation which gives us the magnetic field B being equal to an integral of the magnetization vector integrated with this kernel function over our volume of magnetization. So when you look at this expression, you can see that B can be derived directly from M, and this is indicating that this magnetization M is the natural parameter for magnetic field inversion. Now, in geophysical studies, it's customary to consider the rock magnetization as having two sources. One of them is the induced sources in the rock, and the other are remanent sources. And in conventional susceptibility inversion, we assume that the remanent magnetization is explicitly zero, and we also assume that the magnetization vector is proportional to and in the same direction as the Earth's magnetic field, the inducing field. And both these assumptions are quite often violated in practical exploration geophysics. Now I want to talk a little bit about those the effects of those two assumptions. Firstly, let's consider induced magnetization only. And under the susceptibility approximation, the assumption is that the magnetization is in the same direction as the inducing field. So for induced magnetization, let's consider this elliptical body, this prolate spheroid, and it might represent either a grain or anything up to an ore body. And what we know is that if the inducing field is in the direction of this orange arrow, the actual induced magnetization will be in a direction more like that shown by the yellow arrow. So what happens in this case is that the inducing field direction gets rotated along the long axis of the magnetic body, and so that the magnetization direction is in terms of the yellow, in the direction of the yellow arrow. So this demonstrates a fundamental failure of the susceptibility assumption, which requires the yellow and the orange arrows to be in the same direction. So now let's see what the effect of that would be on a susceptibility inversion. What I'm showing in the left slide here is a TMI over a buried magnetite ellipsoid, and what I'm showing in this shorter arrow is the direction of the inducing field, and what I'm showing in this longer arrow is the actual magnetization direction. You can see that it's rotated into the direction of the long axis of the ellipsoid, and because the magnetization is rotated into this direction, the TMI that arises from it is also effectively that which would be generated from a magnetization in this direction. Now, if we run the susceptibility inversion, making the assumption that the inducing field and the magnetization direction is or are the same, then we'll recover this model shown on the right. What you can see is that the model has a higher zone on the right-hand side, a lower zone on the left-hand side, and really does not show you any reasonable representation of this ellipsoid. And that's to be expected because the approximations that have gone into the susceptibility inversion are not satisfied in this instance. I want to also draw your attention to the fact that even though the ellipsoid is in the upper part of the model, the distortion that occurs in the susceptibility inversion propagates through the a much larger region of the model, certainly a lot deeper and out to the sides of the ellipsoid. So this shows that the distortions are actually global in nature, and it makes it much harder to interpret susceptibility inversion when these effects are going on. So from this simple analysis, you can see that even when we're only considering induced magnetization, there are a number of situations in which susceptibility inversion will fail, and that's whenever there is any sort of geometrical anisotropy in the Earth and significant susceptibility, so things like banded iron formations, magnetite-rich VMS deposits, spiritoite-rich metasediments and sulfide ores. You can see the list here. So we definitely need to work toward using a magnetization vector inversion to overcome these effects. Now, the next thing I want to talk about is remanent magnetization, and The remanent magnetization in most rocks is going to be quite different from the present Earth field direction. So it's clearly a violation of the susceptibility approximation, and what we do in geophysics is usually or often describe the remanent magnetization in terms of a Königsberger ratio. That's the ratio of the remanent magnetization to the induced magnetization, and this typically varies from anywhere from a very small value up to 100. As I mentioned earlier, remanent magnetization is now being recognized as far more important in regional data than we previously thought. A good paper on this is Suzanne McEnroe's paper on crustal magnetization and laminar magnetization in the journal Elements. So now let's look at a simple example of magnetization vector inversion in the case of remanent magnetization. What I'm showing on the left-hand side here is a simple model, the obligatory prism in a half space, and what I have is a remanence direction shown by this blue arrow. I have an inducing field of the Earth's field in the vertical downward direction. These directions are simply shown to make the interpretation of the results more easy to understand. And if I calculate the total magnetization vector in the model, it becomes a series of vectors pointed in the easterly direction, and these vectors are represented by the green cones. Now, when I calculate the TMI response over that, I will recover an image which looks like this, which has a dipolar nature and is what one would expect with an easterly oriented magnetization vector. Now what I'm going to do is show you a series of slices through this, section slices through this model, and we'll be comparing inversion results on that section. And if I slice the model through, what I have is a prism in a uniform Earth. In this case, the Königsberger ratio has been set to 1.4. Now, if I took the TMI that I'd computed over that model and I tried to invert it with a susceptibility inversion, clearly the inversion would fail because the magnetization direction is completely unrelated to the inducing field direction. And that's indeed what happens. Again, notice that the failure of the inversion is not only local to the anomaly, but propagates through large volumes of the Earth model. So when you see this type of large target propagating deep into your model, it can quite often be caused by some failure of the susceptibility in some assumptions. Now let's turn to the magnetization vector inversion process itself. I won't go into this in detail because it's been covered by several other presenters in this workshop. Basically we have the expression which defines the magnetic field that we measure in terms of the magnetization in the Earth, which is the quantity we're trying to recover. The way we recover M from V is by forming an optimization problem. We define two terms in that optimization problem: a data misfit, so that is given a current model, how close is the response from that model to the observed data. And then we also define a model structure measure, which basically says, given a particular model, how much structure does that model have? And by minimizing the data misfit, or optimizing the data misfit I should say, so that it's appropriate, and ensuring that the model has a minimum structure, we're able to produce a minimum structure inversion. So, and that is what's expressed here. Basically we add the two terms together, the data misfit and the model structure with a weighting, a trade-off parameter, a regularization parameter mu, and we adjust that parameter mu so that the data misfit is satisfactory. We might also implement conditions on the model itself that is perhaps it, for example, satisfies some upper and lower bounds or something of that nature. Now, in Foxy, we've implemented this as an MPI-based algorithm. It uses domain decomposition to spread the calculation across nodes in the cluster. We use Krylov solvers, and we actually, rather than implementing this on a specific cluster hardware, we've implemented it in the Azure cloud with an auto-scaling process so that the resources required from the cloud are constructed on demand to solve a problem of virtually any size. So let's now take a look and see how that magnetization vector inversion would work on the simple example that I showed you. Here is my true model, again with the magnetization in the easterly direction. This is the TMI, that is response that this model gives rise to. Now we will try and invert this with the magnetization vector inversion. Again, on the left for your reference is the true model. On the right I'm showing the magnetization vector inversion recovered model. And when you run a magnetization vector inversion, you are solving for both the magnetic field amplitude and direction. The magnetization vector amplitude and direction, and that's represented here by these green cones. So what we're seeing is that the magnetization vector inversion recovers the direction of the true magnetization quite well in this domain and localizes a target body in the volume associated with the true model. So this is a very encouraging result and demonstrates that even though we've allowed the extra flexibility of the magnetization vector inversion to recover both direction and amplitude, we're still able to localize the target effectively. Of course, we are not the first workers to work with the magnetization vector, trying to invert it. Back in 2005, there's an example from an area over the Japanese Trench where the authors have used magnetization vector inversion to try and map out different geologic domains, and they've been successful in doing that here. There's also work in 2009 by Peter Lelever and Doug Oldenburg on using this type of inversion when significant and complicated remanence is present, and you can see an example of their results here. What we've actually found when we've applied these methods to exploration is that looking at the vectors themselves can be challenging. This is basically because it's very hard to view vectors in a three-dimensional volume, and also the vectors' directions themselves change from location to location, and it's hard for the eye to actually follow the changes easily. So what we've found is that if you want to use this method in exploration, practical exploration, there are a number of attributes from the recovered vector model that it is much easier to interpret. And the most robust and useful of these is the amplitude of the magnetization itself. That quantity is the amplitude of these vectors, and is robust and very informative. We can go further and try and extract some information from the directional component of the magnetization vector, the recovered magnetization vector, and two quantities that we've found to be useful in certain instances are the component of the magnetization vector in the Earth's field direction. That's the parallel to Earth field direction component, shown here in M, and that is a component of the magnetization which might be resulting from the induced component. And on the other hand, we can also look at the perpendicular component to the Earth's field direction. So that's shown here. You can see this is largely perpendicular to the Earth's field direction, and that perpendicular component would be indicative of, largely indicative of, or could be largely indicative of remanent magnetization. So now I'm going to come back here. This is the vector model that I'd recovered. I'm going to slice through that model, as I'd mentioned before, and I'm going to compare the derived quantities that I've just talked about, the amplitude of magnetization, the perpendicular component of the magnetization, and the parallel component to the Earth's field. Now, in this top image, in image A, I'm showing you the true model. In image B, I'm showing the corresponding slice representing the amplitude of the magnetization vector, and you can see that that actually targets the model very well. This is a straight smooth inversion of that, and we could focus that up and make that a sharper image, but this is the basic smooth result. So that's very good localization of the remanent magnetization. In this component C, I'm showing the component perpendicular to the Earth field, and you can see in this instance that C and B, the amplitude and the perpendicular component, are almost identical, indicating that in this example most of the effect comes from remanent magnetization, and that is shown here. And in this image I'm also showing you the parallel component. Now this color scale is an order of magnitude more sensitive than these other color scales, so this is actually a very, very small component of the magnetization. Indicating that there is very little component in the Earth's field direction. So if I were to compare the magnetization vector inversion with susceptibility inversion, in this particular case I've shown you these results. I'm just presenting them here as a summary. Here's the true model. This is the magnetization vector inversion. And here is the susceptibility inversion. So again, you can see that the magnetization vector inversion provides a much better model to try and interpret than the susceptibility inversion. And as I'd mentioned before, potential field inversion is, let me say, flexible in the sense that because of the non-uniqueness in the inversion process, it's possible to fit a single set of magnetic field observations with a wide variety of simple models. So if you have poor assumptions going into your inversion process, you're still able to fit the data, and you'll still get some model out, but it can lead to dramatically misleading types of interpretation, so that, for example, in trying to interpret this image compared to this one is clearly a problematic situation. So now let's come back to the magnetization vector inversion applied to anisotropy and demagnetization. I'd shown you this image earlier. This is the TMI over the magnetite ellipsoid, and this was the susceptibility inversion. And you can see the high on one side, the low on the other, and this is the true ellipsoid. So this is a very poor recovery of this model. Now here's the magnetization vector inversion result for that same ellipsoid, that same data, and you can see that the recovered model is a much better representation of the true ellipsoid. So this is just confirming that in the case of either demagnetization and anisotropy, or in the case of remanent magnetization, magnetization vector inversion is a much more robust and better process to use. And I've just summarized that as a table here. So what we've found, our experience has been that it's good to apply this magnetization vector inversion to all survey data. I want to show you now some examples of how to use this in an exploration context. I'll first show you an example from the San Nicolas deposit. In this example, I'm going to show you how magnetization vector inversion works over a more complicated target with remanents. I'm going to again compare magnetization vector inversion with susceptibility inversion. I'll show you how we can sharpen up a magnetization vector inversion image using iterative reweighting inversion. I'll then demonstrate that constraints can be incorporated into magnetization vector inversion, and I'll show you some component images, so the amplitude and the perpendicular and parallel components that I discussed earlier. Again, this work is based on a deposit model developed by Myra Geosciences as part of the a Camiro project. And we thank Tech and Gold Corp for supporting us in this work. San Nicolas itself is situated in central Mexico. I'm showing it here. And the deposit model that was built for that, I showed this image earlier. It's a VMS target in a layered host. What we're doing, these are the physical properties associated with each of the units in the model, and what we're going to do is for the purposes of this exercise, we're going to give a Königsberger ratio of 1 to this target, to the ore zone. Now, Q equals 1 is not certainly not unreasonable in these types of situations. So here's our exploration problem. We're going to define it as follows. We're exploring for a VMS style deposit. We've got a susceptible ore zone. We're aware that there may be some remanent magnetization, but we don't quite know what it is. We're going to say that the host rock is far less susceptible than the ore zone. We're going to add some constraints into this exploration problem. We know there's about 200 meters of sediment cover, so the ore zone has to be in the bedrock and is therefore excluded from this cover process. So what I'm showing here on the right is the yellow surface, which is the base of the sediments. So the ore zone is excluded from the base of the sediments. We also know that there's been some faulting through this area and that our ore zone is excluded from the west side of this green fault that I'm showing here. So now we have some TMI data on 150 meter line spacing and at a clearance of 100 meters. I'm showing that here in this case. And now I'm going to do an unconstrained inversion for both magnetization vector inversion and susceptibility. On the left, I'm showing the amplitude of the magnetization vector inversion, and on the right, the susceptibility. And you can see in the magnetization vector inversion that the general character of the deposit, or the ore zone, which is shown here by this wireframe image, is much better represented in the magnetization vector inversion image than in the susceptibility image. The susceptibility image targets a high-low type of situation, which is usually associated with some sort of remanence effect. Now, what I can do is take my smooth model. I can apply Geosoft's iterative reweighting inversion process, which is a sharpening or focusing process to compact the material recovered by the smooth inversion into a more dense, into a more susceptible and more compact target. And what I'm doing is showing that here. And when you do this process, the recovered susceptibility in this area becomes much greater. Now, I should say that when I refer to susceptibility associated with the magnetization vector inversion amplitude, what I'm really talking about is the amplitude of the magnetization vector scaled by the magnetic field, the inducing magnetic field amplitude. So this would produce a number which is equivalent to susceptibility in the case of induced only magnetization, and is a generalization of susceptibility for the magnetization vector inversion. And we use this number because this scaled magnetization amplitude is a more familiar quantity to exploration geophysicists. Now, in this image, I'm showing on the left here the unconstrained inversion again, and on the right I've implemented this fault constraint in green. I've said the ore zone cannot be on the left side of the fault. It's also excluded from the sediments, so it has to be bedrock target. And you can see that that's easily achieved with magnetization vector inversion, just the same way that it would be with susceptibility inversion. So the point here is that extending the flexibility of the inversion to allow recovery of the direction and amplitude of the magnetization vector does not prevent us in any way from using any of the methods with which we're familiar in susceptibility inversion. If I now look at the zone that's recovered by this inversion, you can see that it's shown here by a brown surface, and the black more structured surface embedded in that is the true ore zone. So what we've been able to do is recover that very effectively using magnetization vector inversion. Okay, so now I want to talk about another example. This is a field data example from the Osborne area in northwestern Queensland. I'm showing Osborne here. This is Queensland in Australia. And what we're going to show in this example is the application of magnetization vector inversion to field data collected over Osborne, and we're going to compare it to the susceptibility inversion. Now, the Osborne mine has been very well described in a series of publications. Briefly, we have significant copper-gold mineralization beneath 30 to 50 meters of deeply weathered cover. Since 1995, exploration is mainly focused on delineating a high-grade primary mineralization that dips steeply to the east. And the current exploration is focused on trying to map that dipping mineralization. So we have the geology from the Osborne area. I won't dwell on that. Here is an image of the pit, and this is the mineralization which is extending deep and to the east of that pit, and this is the area. Mapping this is the goal of the current exploration. Here's the TMI data collected over Osborne. It was acquired in 1997. It's good high quality data, shown it's flown at a 40 metre clearance and with a line spacing of 40 metres. Now, when I take that data and I perform the magnetization vector inversion, and what I'm showing you here is the amplitude of the magnetization vector, you can see that the general feature of this inversion result is something dipping to the east. And what you can see also shown on this image is mineralization, known mineralization from drilling, and you can see that the actual inversion does show a trend which agrees with the known mineralization. So this is a very encouraging result for the magnetization vector inversion, and shows that the magnetic field measured over this area is consistent with this type of model. What I'm showing in this slide is the magnetization vector inversion amplitude again, the same image, and I'm comparing it on the right to the image which is recovered from susceptibility inversion. This is one of those exploration situations where susceptibility inversion was run on the geophysical data, and the model that was recovered really bore no resemblance to the geologic situation, so something was clearly wrong, and what it appears to be in this case is the restriction to susceptibility is inappropriate in this area, and one needs the extra generality and flexibility of the magnetization vector inversion to recover a meaningful model. So to conclude this section on magnetization vector inversion, I've shown that it's the natural parameter to recover when you're inverting magnetic field data, and it involves both an amplitude and a direction. It aids in the interpretation of magnetic field data, particularly in cases where there's any sort of demagnetization or anisotropy or any sort of remanent effect. We've found it to be also effective to look at derived quantities from the magnetization vector output, and the two quantities, or the three quantities that we emphasize are the amplitude as being the primary quantity to interpret the magnetization vector amplitude, and sometimes we can also obtain information by considering the components of the magnetization vector in the Earth's field direction and perpendicular to that direction. So I've shown you that inverting magnetization is robust, and we can use the usual processes that we use in susceptibility inversion for reducing the effects of non-uniqueness, that is regularization. We can include model weighting, constraints, sharpening, all the usual tools of inversion. I've shown you that this can be very effective on real field data from the Osborne deposit, and it has been the experience of the authors, particularly having applied this to a large number of exploration problems, that the magnetization vector inversion often produces a model which is more consistent geologically than a susceptibility inversion. So we would advocate, based on that experience, that magnetization vector inversion should be a serious consideration for